Okay, am I on? Hello? Is it working? Can you hear me? Good, perfect. I'm kicking off promptly just because I've got more than 60 minutes of content to cram into 60 minutes. The first thing you'll notice, there's no slide up. I don't have any slides. I went completely zero slide. I do have, of course, I'm a .NET dev. I've got a little .NET program that tells you who I am and where to reach me. So I'm mostly on Blue Sky for social stuff now, so posting content and things, you'll find me over there. You can also follow me on LinkedIn and get updates about the stuff that I'm putting out as well. I'm Steve. I'm an engineer at Elastic, Pluralsight author and MVP. And today we're going to be talking about unveiling .NET secrets. So there's a lot of people here, which is great to see. Hopefully everyone's read the abstract and understands what you're in for. This isn't a talk where on Monday you'll go back to the office and there's a bunch of things that you'll suddenly start doing in your applications to make them better. You're not going to learn new C# features or performance tips for .NET as such. What we're going to be looking at is a little bit about under the covers of .NET and how assemblies are actually produced and then run by the runtime. And it's mostly an excuse to learn various tools that you may or may not have seen. They're usually more advanced tools, but to see how those get used in certain scenarios and give you ideas on when you can make use of those. So I'm going to jump straight over to a terminal here. And the first thing we'll do is make a directory. And in there, we're going to start by creating a program file. So I'm going to do this in Notepad. So if I can type on this lectern. Wow. It's going to be mostly you watching me fumble typing. So we'll do this. And then we're going to create a CS file. Now, I'm not using an IDE here. Live coding on stage is inherently dangerous for speakers and particularly exciting for the audience. So we're going to attempt to do this without an IDE safety net. If you do spot any errors as we're going through, please tell me, and we will try and correct it as we go. But we're going to give this a shot. So the first thing we're going to do is we're going to use something that's been in .NET since .NET 5, C#9, called top-level statements. And this is basically the notion that in a one file within an assembly, we don't have to create the traditional structure, the rigmarole of having using sort of directives, then having a namespace, then having a type with methods on it. We can actually just start putting statements directly into the file. And this is part of all of the .NET templates today. So if you do a new console app or a new ASP.NET Core app, unless you uncheck the box or tick the box, I can't remember in Visual Studio, you'll get a top-level statements file. And we'll use that just because it's terser. So I'm going to begin in a rather unusual way by starting with a open curly brace here. Let's zoom in a little. Open curly brace. So this is the beginning of a scope in .NET. And the next bit gets a little bit more complex, so bear with me. We're then going to put a closed curly brace. That is the live coding portion of this demo done. I've succeeded. I've done 2 characters from memory, and everyone's pretty impressed. Now, it's not about the code. This is as much code as you're going to see today. It's about all of the stuff that we then do following that. So we've created this program, and then we need to obviously compile this. So we've written some C# code, right? Zoom out a little bit here. We've written C# code. At some point, we need native assembly code, if I can spell assembly. So we need that native code to run on whatever platform we're going to run this application. But when we compile a C# app, at least by default, with the compiler, we don't produce native code. We produce a DLL file, an assembly file, that contains IL, intermediate language. Seemed like a good idea to type this all out, but maybe a slide would have been quicker. So we get IL. IL is a bytecode format. It's part of a specification that's been around since .NET Framework days that defines a set of operations that are, as the name describes, a kind of intermediate language representation. So it's simpler sets of instructions than C#, the high-level language we write in. But the important thing about this is it's platform independent. So we can take this IL code that we've built and compiled on a Windows machine, we can deploy that onto a Linux box or a Mac box, and that code can still run. Because the piece of code that actually converts this is the JIT in the runtime, the just-in-time compiler. So the JIT's job is to take that intermediate language and turn it into the appropriate native instructions on the machine that you're running on. Of course, we need to get to the IL in the first place, and so to do that, we need to compile from C#. And for that, we use the Roslyn compiler platform, and specifically CSC, the C# compiler, which is part of that platform. That's what takes our C# code and turns it into the IL code that's in the file. Just a little note on the JIT. So The just-in-time compiler, in modern versions of .NET at least, has been optimized in various ways. And one of the things that's now enabled by default is this notion of tiered compilation. So tiered compilation is basically this notion that because this JIT has to happen the first time a method's ever invoked in an application, we want that to be reasonably quick. We don't want the JITting time to delay the actual execution of the code that we want to run. And so in tiered compilation, there's a tier 0, which basically does the simplest thing it can. It doesn't do many optimizations. It just says, well, what's the quickest way I can take this IL code and convert it to instructions that will represent that on the platform where I'm running. So tier 0's job is about kind of quick startup time, little sort of delay. But the tiering continues. So after a method gets invoked a certain number of times, there's not necessarily a specific number, it's configurable, I think, in environment variables, we get this tier 1 that might kick in. So when a method's been invoked enough times, the runtime says, well, this is a method that's now being used often. What I'm going to do is I'm going to recompile that in the background and do my best to re-optimize that code to make it as efficient as possible. Normally that's about reducing the number of actual native instructions that need to run so that the code runs a little bit quicker. But there's another technology that's at play here called dynamic PGO, Profile Guided Optimization. And this plays into this tiered compilation model because what it does is it, at tier 0, injects a bunch of instrumentation instructions into that native code base so that it can track specific things about how that code's actually being used at runtime. So for example, it can actually tell which branches of an if-else block, for example, are most regularly taken. And then later on, at tier 1, that information can be used to actually optimize the instructions that are written so that it can optimize for the common case. So if, for example, you have an if and else, but 99.9% of the time the code flows through the else, then it makes more sense to check that condition first in the native code and then immediately run the code that normally follows it. And then the slow path is for that sort of 0.1% that occurs after it. Now, there's one other point to mention here, because we're sort of talking here about the common compilation of .NET, but there's also sort of other modes today that we have. So we have ahead of time compilation, which is where we can actually compile our application, as the name suggests, ahead of time directly into native instructions. And this can be useful if you're in scenarios where you need very rapid startup. Then obviously if you've got no JIT needing to run as part of that code base, then things are going to run a little bit quicker. There's also kind of a middle ground technology called ready to run. That's also an option that you can do with .NET as a switch when you're building. And ready to run is kind of the best of both worlds. So it includes native instructions, and those are the ones that run the first time those methods get invoked. But behind the scenes, the IL is still present in that file, and that means that the JIT compiler can still do its magic over time to try and optimize based on how the application is being used and replace the code base. So we've got our program here. We need to turn this into a DLL, basically. And normally we'd use .NET build, right? If you're using the modern .NET, you'd be using the .NET command line, .NET build, and then behind the scenes, that will trigger MS build, and then at the end of that, you will get your DLL file and a few other files alongside it. We're going to do something that you will never do in your day-to-day job, and invoke the compiler directly. Can everyone see that okay at the back? Hands up if you can't. Cool. I've got a thumbs up, which confused me, but that's fine. Okay, so what I'm doing here is I'm using the .NET executable. And if you haven't sort of explored, this is a Windows machine. It will be different, obviously, on Linux. But on my Windows machine at cprogramfiles.net, I have a .NET exe in the root. And this is the main entry point for all things .NET on a modern sort of .NET platform. You can see it's not a big file. It's 150K, so it doesn't actually have much knowledge in it. And if you explore what it actually does, it just has enough knowledge to go off and do the right thing depending on the arguments you provide. And that's why it's referred to internally as the muxer, or the multiplexer. Its job is just to figure out, okay, I need to route this here, or I need to route this there. So one of its jobs might be to actually invoke the runtime to load an assembly and start executing. But other jobs that it does is also an entry point into running SDK commands from the .NET SDK, or even things like invoking MS build directly. So we're going to be doing that, and that's on my path, so obviously I can just do .NET here. And then the DLL I'm actually going to execute here is here. And you can see this is in program files.NET SDK. It's in the version 9 of the SDK, so I've got the latest SDK installed on my machine. And under there's a Roslyn subdirectory. And Roslyn is that compiler platform for .NET. And one of the things it has in it is a CSC DLL, which is just a managed DLL. This is if you go and look at the source code in Roslyn, the C# compiler is written in C#, which gets kind of inception-y. But that just produces a managed DLL, which is the entry point to trigger the compilation process. So what we're doing here is just saying to .NET, we just want you to launch that executable directly. Now, when we do a compilation, this is one of the reasons you wouldn't do this at the command line typically, is we have to give it a bunch of additional information. Now, our application has 2 characters, right? It's not particularly complicated, but inherently, we do need to actually reference some stuff from system runtime just for the nature of .NET, because there's little attributes and things in there. There's the base type of like object, for example, that need to be present. And so when you compile your code, the compiler needs to be able to check anything that you're going to be referencing to see that any methods that you're invoking through your code compile, right? That you've used the correct signatures, the correct set of arguments, etc. And so the compiler needs those references. And you'll see that this is coming from .NET Packs on my machine as part of the SDK installation. And in there's a folder here that's Microsoft.NETCore.app.ref. And this is the reference assemblies for .NET. So there's kind of 2 types of assembly. The ones we normally create are the regular assemblies that include all of our code, all of our implementation details, and the actual stuff that's going to get run. But for compilation, the .NET team, as part of the base class library, ship these reference assemblies, which you can think of as a very light assembly footprint that just has the public signatures for the types and the methods that you can invoke on those types. It doesn't have any implementation. And that's all the compiler needs to compile code, because it just needs to check that you're calling valid method signatures. It doesn't need the implementation detail. When you actually run your application later on through the runtime, then that's when the real assembly gets loaded as part of the assembly loading process, and that's where the implementation code gets run. So it's typical to just compile against those reference assemblies because they're smaller. I'm going to optimize the code, which basically means I want a release build. I want the debug symbols, so the PDB file, which allows us to map from high-level C# code down to the code that's executing at the IL and native level when we're debugging later on. For the output, I just want a DLL file, and my input for this compilation is program CS. So for a single file, there's quite a lot we have to type. This is obviously why we don't use the compiler directory directly in our usual day jobs. We use MS-build, which is much more convenient for such things. But I'm going to run that and list what's in the directory here. So we have our program CS file, 2 bytes, not much in there. We have a program DLL now as the output, which is the minimum default size seems to be 4K. And then we have a PDB file with the symbol mappings. And that's enough, in theory, to run an application. So what we might want to do next is actually start the application. And so I can, again, use .NET to say I want to invoke this DLL. Because it's an executable DLL, it should run, right? No. We get a big wall of error. But it actually tells us a lot of interesting stuff about what .NET does under the hood. So yeah, it's a fatal error. It's telling us the library host policy DLL required to execute the application was not found in this directory, which is true, yeah? We didn't create that file. So let's continue, because it will tell us more. So it's failed to run as a self-contained app. The application was run as a self-contained app because program.runtimeconfig.json was not found. Now again, we didn't create that, so that's fair enough. It's correct so far. If you want to run this as a framework-dependent app, add that file and specify the appropriate framework. So the 2 things here that are particularly interesting is this notion of framework-dependent and self-contained. Framework-dependent means that when you build your application in the output directory, you have your DLL file for your assembly that you're building, and you also have any DLLs that you reference that aren't part of the base class libraries, maybe from NuGet packages. And that's all that you produce. And so in order for those to run, they need the runtime to be available somewhere on your machine. And that, in modern .NET, is in that program files.NET folder for .NET on Windows. And that would include the runtime and the base class libraries for each of the versions. So again, we can hop over here, and we can see that we have the SDK folder, but we also have this packs, and this contains a bunch of the reference assemblies, and then there's this shared folder, and here, for the different sort of targets that might be available, we have a bunch of the files that we'd expect. So this includes all of the base class library DLLs and things, but it will also, in another directory that we'll see later, include all the runtime files as well. And so framework dependent is the common scenario. One of the advantages, it's a small unit to deploy. We only have to deploy generally a relatively small number of files to wherever we want to run code. Obviously, the downside is you need the runtime installed, which is pretty trivial with modern .NET. We can have .NET versions side by side on the same machine, and that all works nicely. But the alternative is we can have a self-contained app, and that's where we build in a particular mode. We put a flag on our build that says we want to be self-contained. And in that mode, we expect to build not only our assembly, but also we want a copy of all the base class libraries that we need, and also all of the actual runtime, the native code for the core CLR, the common language runtime of .NET, and all of the relevant components like the garbage collector, the JIT, for example. And so in self-contained, the expectation is we have all those files in our output directory, and we can deploy that somewhere and run it without having had to do a framework install on the machine. It means a larger install footprint. It's not particularly convenient for most people, but it would be maybe useful in, say, an enterprise environment. If you've got to deploy an app to hundreds, maybe thousands of machines, that's a Windows .NET application, maybe you don't want to have to pre-install the runtime on all of those machines through something like group policy and then manage the updates and things. You just want to have to deploy the app, and so that may be a choice where you go self-contained. So the other thing that's highlighted in here, so not only is it running self-contained because that file isn't present, but it also hints at the actual error is it can't find this host policy DLL. And this is one of the critical DLLs as part of .NET that's responsible for actually booting up the correct version of the runtime and loading our assemblies and actually getting things working. And it expects that to be present because it assumes it's self-contained. So it's checking here to say, well, if it's self-contained, I should have this critical file, but I don't. So the way we're going to deal with this is that we're actually going to, for now, make this a framework-dependent app and create this program.runtimeconfig.json. And I'm going to steal a snippet just to save typing, my only snippet, hopefully, of the session, and just put this code in. So this is the minimum information we need in there, and it specifies that we want to be defining the framework that this app runs on. We're using Microsoft NetCore App, which is just sort of the legacy name from the NetCore era. And specifically, we want to be on the runtime version 9 or any of its kind of patch versions. So that should be enough now for us to run this application, and now we don't get the error. And we can check with last exit code. We get exit code 0, so the app ran to completion. There were no errors. Obviously, we don't actually have any code in our application, so that's what we'd kind of hope. So the next thing I want to do is have a little bit of a look at what's in a DLL file. And for that, I'm going to use a decompiler from JetBrains called .Peek. And I'm just going to drag in the DLL that we've just created into there and expand it down here. So inside a .NET DLL, the structure of this file follows a convention from Windows days, from back in sort of the .NET Framework days, where the spec for .NET Framework was defined, which is the PE file format, which is a very typical Windows file format to use for executables and libraries. And most sort of executables will follow this convention. Now, although that's a Windows file format traditionally, this doesn't mean this DLL can't be used and run on Linux, because the thing that's actually going to read this file is the .NET runtime. And so it just knows how to parse a PE file format, find the bits that it cares about for running .NET applications within there, and then actually launch your code. But we can expand in .Peek, we can expand this metadata folder and start to see, let's try and get these windows a little bit clearer, start to see some of the content inside this file. So if we expand headers, you'll see some stuff that's obviously legacy Windows era naming. There's a DOS header and NT headers. We're not interested in those. Within a PE file, it defines sections, and the section we're interested in is .text. And .text will contain all of the executable code inside this DLL. And we can see that there's another header here that we're getting to see, which is being read in. And this is after inspecting that text section and finding this CLI header, the Common Language Infrastructure, which is the header defined in the original spec for .NET Framework that defines the entry point really into the .NET world within this file. I'm going to expand that. There's not much that we actually care about in here. Can everyone see that? It's probably a bit small at the back, right? Yeah. Let me see if I can zoom this and not lose my place. The only actual piece of that I care about is the fact that in there's this thing called entry point token. And that says to .NET, when you launch this assembly, this is the token for the method you should invoke. And so that's encoded into that header. Now, if I scroll down and come down to here, we can see, I should show you the numbers, I suppose. So it's saying within the metadata for .NET, most of the metadata is organized into what they call tables, which are simple sort of data structures that represent all of the types and members that we have in the file and also those we reference. And so it's saying you can find the entry point in table 6 at row 1. So I scroll down here, we go to table 6, which is listed here. So that's the method def table, the definitions of all the methods within our assembly, and we'll expand that. And we can see that indeed there's 2 methods, and row 1 here is program main. Main's got an unusual name, but don't worry about that for now. So the first question some of you are probably and hopefully asking is, well, where did that come from? We just created an open scope, closed scope, right? We didn't create a main method or anything. Let's actually look at the code a bit further. So if I come down here and expand the actual root namespace here, we can see the types, the classes and things defined inside this assembly. And so we can see that indeed there is a program type here with a main method. And if I double click that, and now I may have to zoom out. If I double click that, there we go. On this side, we get an example of what's in that class, what's in that method. So we didn't create this, but the clue is the fact that we've got this attribute here, compiler generated. So the compiler put this into this assembly on our behalf. And this is a process known as lowering in the compiler. Very common in all compilers. You have these high-level language features that are available in C#. Most of those will be converted into simplified forms that still conform to C# that the runtime knows how to execute and run. And so this process happens all over the place in our code. If you use the var keyword in your methods, as everyone should, if you use the var keyword, the actual compiled code will replace that with the actual type name. It's the convenience in C# that we can use var instead of defining the type directly. But the compiler actually converts it because var doesn't exist in the runtime. It doesn't exist in the opcodes for the IL instructions. It's just a notion in C#. So every year, Mads and the team, they bring out these great C# features, adding in things like top-level statements or ternary conditional operators or all variety of those things that are convenient terse C# code. Most of those, nearly all of them, don't require changes in the runtime. They just changes in the compiler to tell it, how do I convert this concept, this new concept you define for the language, into a lower form of C# that uses older style syntax or simpler syntax. Even things like for each loops will get expanded normally to something like a while loop, for example. So we don't see this, but what the decompiler's done here is it doesn't know that we just wrote open curly brace, close curly brace. It's taken the IL instructions that it sees, plus the metadata in the file, and reconstituted what it can see from that data. So the main method here has a weird name just to avoid kind of clashes with any main methods we might define in our app. And you can see it's empty because what would happen with top-level statements is any of the stuff that we write in that top-level statements file would be put in as the method body for main. So it's still a regular application that .NET knows how to execute. So we've got an idea now of the C#. We've got the main method, and obviously there's a parameterless constructor that's kind of implicitly there as well. If we now jump over to IL, we can look a bit further. And so IL code, semi-human readable, this form. This is not how IL code is represented in the file. The file has a particular layout where IL code lives in one place, metadata lives in another, and what .peek's doing here is just joining the 2 bits together for us so that we can see in a semi-human readable form what's in that file. So if you squint, you can see there's a program class which is defined here, extends system object, as all classes do. Don't worry about all these weird keywords, which are part of the kind of the CLI spec that we don't have time for today. But the ones that we'll look at are these actual method definitions. So this is the method definition of the main method. So we can see it's a method, static void, it's called main, with these characters around it. It's got a string array of arguments, and it's CIL, Common Intermediate Language, managed code. It has the entry point token sort of slapped on it here because that's present in that CLI header, so we know that this is the entry point into the app. The max stack, again, we don't really have time to go into the stack frames and things, but the stack, the evaluation stack here, but this is just saying that the maximum this stack can grow to is 8. We're not using the stack really here. We're not creating local variables or anything like that. The piece we care about is this IL instruction. So this is the IL instruction that empty method turns into, which is just the ret IL instruction, which means return from this method, basically. Potentially passing back a return value, but we're void returning, so we've not got anything to return here. And this here is just a logical label. This, again, isn't in the DLL. This is just telling us at offset 0 in the bytecode for this particular method, you'll find this instruction. The constructor code is a tiny bit more complex. It's 3 arguments. So it's saying here, the first instruction is load arg0, which is a shortcut for loading the first argument at index 0 off the evaluation stack for this method. Now, you'll see this is parameterless, so why do we even have an argument? The reason is that there's an implicit this argument, which is the object, the instance of the thing that we're operating on, that's passed into any instance method. And that's passed in a kind of hidden way as index 0 of the evaluation stack. We then have a call instruction, and the call instruction is calling a particular method, in this case, the constructor on system objects, so the base constructor. Now again, this isn't what's in IO, it's not written in like UTF-8 text or anything. The call instruction is followed by 4 bytes that represent the token within the metadata of the method that you want to invoke. We'll look at that again in a bit more detail in a moment, and then it returns. We can see that that call instruction is more than 1 byte because it starts at offset 0 in the bytes, and the next instruction starts at offset 6. So DotPeek's really useful for taking any assembly that you have, even if you don't have the original source, and getting close to what the code is that you could write to re-represent that file. The next thing we're going to do is go a little bit deeper. And what I want to do for this is actually look at the bytes in the DLL file. So the way I'm going to do this is over here, loaded in Visual Studio, I've got a little tool. I've got links to this in the resources for the talk that I'll reshare the link just before you go. This is a tool from someone called Kirill Ozenkov, who works for Microsoft. He works on the tooling team. He's built a lot of kind of lower level developer tools at Microsoft. This is just a free open source thing that he put out actually just like a few weeks ago, and I thought, perfect, this will be a nice thing to show today. And what this does is it takes a managed DLL file, so I'm directly passing in my program DLL file that we just produced, and it inspects that PE file, parses it basically, and then parses through the .NET portion of the data below that and represents information to us. So one of the things that we can do with that is say, after we've got the PE file parsed, I want to access the text section of it, and I want to find the first child that's labeled IL. And so logically, it will have gone through the metadata and the IL instructions that it finds in that PE file at the known locations based on the spec, and then it will label them so that I can then ask it for information about them. In this case, I just want to know where does that code start and how long is it in the file. So I'm going to run this, and it does no output. That's interesting, isn't it? Is it? Did I call it the wrong name when I? Oh, template out. I've used the wrong directory name. Okay, thank you. Well done. That's super observant, and I'll have to come up with a new name later on. Let's use the right path and pray that this works. Hey, thank you. So the IL code starts in this file at 592, so offset 592 into the file. It's 12 bytes, so there's only 12 bytes of IL in here. The only IL that's present in this file is the code that's for that program class. Anything for like system runtime, etc., those live in the other assemblies, so we'd find those in those DLL files. So if we actually then open up a hex editor here, I'm using HXD, you can use whatever you fancy, and we go in here and pull that program file in, and I go to offset, it's the decimal offset that we got from that file, so 592, and it jumps down to here. Let's zoom in again. So it jumps down to here, and if I look at this, so 4 bytes, 4 bytes, 4 bytes. So that's the IL code bytes in this file. Now, there's 2 null bytes at the end here, so these are padded to 4-byte boundaries, so actually the IL we care about here is that. And if I zoom back out, we pop into Notepad, and if I paste that in here, let's decode these bytes and just double check how this kind of works. So the first thing we need to know is like, how are these bytes laid out and what do they mean? And for that, there's if we go to the spec file, so these are available online. If you search ECMA 335, you'll find the original or the latest version from like 2012 of the .NET Framework spec for the Common Intermediate Language physical layout. And this still applies today for the most part. And so the key bit here is it's telling us a method consists of a method header immediately followed by the body, possibly followed by extra data sections. There are two flavors of method header, tiny and fat, which is not great naming. The least two significant bits in a method header indicate which type we are dealing with. And for a tiny header, the header is 1 byte long and stores the method's code size in there. So it's saying here a method is a tiny header if there's no local variables involved, the stack doesn't need to go above 8, there's no exceptions that this method deals with, etc. And then it tells us a little bit further down that in the tiny format here, the size then is encoded in the remaining 6 bits. So we can use this and say, well, 006 is 000, 0110, hopefully. And if I then look at this, so these are the least 2 significant bits, a value of 2 here. And if we check the spec, which I've lost there, value of 2 means we're dealing with the tiny format. So we know we're in a single byte header that represents what's in this file. The remaining bytes, and we restart at 0 here, so the remaining bytes tell us how long it is, so we've got a value of 1. So our actual instructions here is just 2a. And 2a is, if we check in the spec again, we can go to further down in the spec, we can find all the opcodes, and so 2a down here is ret. So this is what we saw in the decompiler, it shouldn't be too surprising. So this is our empty main method represented as IL. Just for fun, we'll do the other one. So we've got 1e, so 0011110, hopefully. And again, we check, so this is still a tiny header, value of 2 here, and now we've got 1 plus 2 plus 4, which is 7, 1, 2, 3, 4, 5, 6, 7 bytes. This is what we'd expect. We start at 02, which if we scroll up on here, 02, load arg0, again, not surprising. It was followed by, I should have memorized what the next one was, 28. A call instruction. And as I said earlier, and if you look further in the spec, it will tell you that for a call instruction, we then expect 4 bytes to tell us what we want to call. And so if we go back to this code, and it's in little endian format, so this is the 4 bytes that are the token for what we want to actually call. And in this case, the table is this byte here, and then we're row 6 of that table. So 0A is the table. So if I expand the metadata again, scroll these windows a little bit, and probably zoom that. So 0A is the member ref table. So this is not members we define in our application, it's members from referenced assemblies. And expand this row 6, the constructor for the object. So this is how it knows by looking at the metadata now, this is what you actually want to call. And then if we go back to the file, we have a ret instruction at the end. So this is exactly what we saw in .peek. We've just gone really, really low level with it there. Right, what do we want to do next? Let's go into WinDbg. So we're going to use WinDbg for the next bit, just so we can debug through this code. The reason I'm using WinDbg is that it's a more advanced debugger than you would maybe get in Visual Studio. And it lets us do native and managed debugging in the same logical session. Visual Studio is actually pretty good for a lot of that now, but WinDbg is a tool that's worth knowing about if you get into really gnarly situations. It's a free tool. It's actually on the Windows Store now, so you can just get the Windows Store app, and it's slightly better than it used to be. And I'm going to use this. So typically, you just use Visual Studio for managed code debugging. So I'm going to launch an executable, and because I've screwed up my naming, that's going to be template app now, isn't it? Make sure I run this in the right directory. So I'm using the launch mode here. I'm saying advanced because I want to actually invoke .NET.exe with this argument, the DLL that we want to run. So that's just the same as what we did over here when we did .NET program DLL on the command line. And this is the directory, my working directory that I want to start in. And then we'll start debugging. So the console loads because the app has launched, but it's paused really early, pretty much just after the thread creation for this process. So the debugger's broken in at that point. And you can see we're kind of pretty low level in the stack here. We're in NTDLL in the native code. But you can see that .NET.exe was launched. See if I can zoom this a little bit. .NET was launched, and then obviously to load a process on Windows, there's various libraries involved, NTDLL, kernel 32. These are the things that can spawn the process and the threads and things. So we've broken really early. What we want to do is kind of move on a little bit further into this app. We want to know once the runtime's up and running, and we want to be able to debug further. So what I'm going to do here is a command that lets me say, I want the debugger to break again when a particular module is loaded. And the module I care about is CLR-JIT. CLR-JIT is the just-in-time compiler. So I know that by the time this module is loaded, the runtime is up and running. It's already loaded our assembly and started loading the types and things, and it's now ready to invoke a method. And in order to invoke that method the first time, it's going to call out to the JIT and say, right, compile that IL code into the native instructions, please. So I do that and press G, and that continues into the process. And we see a whole bunch of additional modules start to get loaded now. The most crucial of these is, it's here, is the host fixer DLL, host framework resolver. And this has been loaded from the shared sort of runtime files on my machine under the .NET directory, under this host FXR. And you'll see if I go into that directory, there's not a whole heap in there. There's one of these for each of the runtimes I've got installed on this machine. And in 901, it's just one DLL. And what this DLL knows how to do is actually locate the right version of the runtime files to start loading, based on configuration, for example, that we've put in that runtime config.json file that sat next to our DLL. So this just tells it, this is just sort of responsible for the early location of the runtime files. And so .NET when it gets past a DLL as the first argument, basically just calls out to this library. And it's a native library. You could use this in your own native apps if you want to launch .NET applications yourself. You could actually call into this and follow the calling conventions for this file. Host fixer does a bunch of stuff, but eventually it loads host policy DLL. We'll call host policy DLL from earlier in our error message. Host policy DLL is the main library that knows how to actually sort of locate, prepare, and actually launch the .NET runtime and pass our assembly into it. And so it does a lot of stuff about actually kind of kicking off the runtime itself. So host framework resolver just locates the right version of that to use, and it's in this case resolved to the folder in version 9 because our app targeted .NET 9. So in that target framework we had in the runtime config, we said we wanted version 9, so it finds version 9 of the host policy, again, in my shared directory, so the shared runtime files that get installed with the runtime. And then host policy, soon after, calls into core CLR DLL. So this is where we launch the common language runtime of .NET itself. Bunch of stuff, bunch of stuff, bunch of stuff. And then we get to here where we actually start to see managed libraries are now being loaded into this application. So system private corelib, which is the kind of base class libraries, and then also system runtime, because we took a reference on that for things like system object. And then it broke here where the JIT got called. So at this point, we've just loaded the JIT. And I'm going to run another command here, name2e program DLL. So I'm going to say, look, within the program DLL module, I want to inspect that main method, using that weird naming that they use. I want to inspect the method information that's contained in that DLL file for that. And so that gives us a bunch of stuff, and it says, okay, here's the module. The module that exists is usually one module per assembly. And here's the name of that thing. And critically, we can see not JITted yet. So the just-in-time compiler has been loaded. It hasn't yet run. We haven't converted our code that's in IL to native code yet. If we click on this link for method description, we get a bit more stuff. And this just saves you writing these commands that you could do by hand yourself, but these links make it a lot easier in the modern version. I'll scroll this down a little bit. And we can see here that it gives us some other stuff. So yeah, not JITted. Current code address is empty because it hasn't JITted native code yet. But we can see where the IL code lives. And if I click on this one, we'll see indeed it can print out the instructions that live there. And I can even grab that address, come over to this memory dialog here and load it in. And down here, it's a bit small, we'll see this is the memory of this process. And we can see 062A. So that's that method that we saw earlier in the DLL file when we looked at it in the hex editor. Now it's been loaded into memory. So part of the assembly loading process is to load the IL code into memory, put it at a particular known location, at a particular offset in the memory, and then that can be found when the code runs through the just-in-time compiler. The other thing I'm going to click here is this other link to set a breakpoint when the main method gets invoked in this application. So it adds breakpoint. I'll press G to continue, and it goes a little further. And now we can see some other output. We can see the program's been JITted in that particular method. So we hit our breakpoint, and on the left-hand side here, because we have the symbol file, the PDB file, it's able to load the symbols up and actually work out where in our actual code we are now in this empty scope, which is particularly unexciting. But what we can see here is that we have a JITted application. And what I'm going to do here is I'm just going to rerun actually that, where is it, name to e here. And now we can see that if we get the information about this method again, now we get a JITted code address. So if I click this, I can now see the assembly instructions that the just-in-time compiler has produced to actually execute that. We're not going to go into assembly code, you'll be probably pleased to know. This just pretty much represents an empty function. And it's not the most efficient code. So if we actually look at the method description for this, you'll see it now tells us the code address quick JITted. What this is short for is tier 0, so the not optimized JIT code. If this application was running and it was calling main often, which it never would, of course, that code would eventually go to the tier 1 code, and that might be optimized further. For example, it might choose to actually just make that a ret instruction in assembly code instead of dealing with things, because it can see that the arguments that get passed in, the string array of args, is never accessed, so it could optimize away the code in that stack frame a little bit. So yeah, that's pretty much it in here. The last thing I'll show you, just so you know it's there, so if you're doing this level of debugging and you're running into sort of applications where you want to explore them in this debugger, what we can do is something like dump heap here and say, show me the managed heap for this application. It's all getting a bit small, so let's see if that's a bit better. So what this does is dump literally all the objects currently on the heap for this app. So it tells me their address, I get a link to the method table for those, and the size of them. We can also see it down here organized by sort of type. So for example, we can see at this point in the app there are 42 strings loaded into the heap. Now we didn't load anything in our code, of course, but things like the runtime code will be using strings as part of its code base, and those are the strings that will have been loaded in there. So we can even click on this if we want to. That lists all the strings in here, and I'll pick one at random and hope it's a useful one. Not click the link, click the address here. And so this actual string just represents, well, it's the path to our app. It just happens to be in there. Let's see if there's another more exciting one here. That's just another path. You don't need to click all these links, but this is the actual value. If these are long, you wouldn't see it printed out here. But it even tells you, you can see the actual kind of makeup of that particular object in memory as well, and what's all the offsets within that in memory for that particular object. So there's an advanced use case there for that kind of thing. Last thing I'll show you in here, if I can just pull this back up just so that we can see it, because it gives us a better picture of what actually happens when .NET ran. So .NET exe got loaded. Let me zoom this in. .NET exe got loaded, and its invoke main method got invoked eventually, goes through a few layers in .NET. Then it located that host FXR library and called into this hostfixer main startup info. That then looked at, for example, the template file, the runtime config file, to find out, well, what version of the runtime does this need? Then it located the correct host policy. That does a bunch of stuff to start up the app, basically prepare and then launch into core CLR. And core CLR says, well, okay, I need to execute this assembly, and eventually I need to run the main method that's within there, or the entry point, finds that token, and then runs the code. So you can kind of see the native call stack, if you will, of the .NET execution there. How are we doing on time? We have time, so that's good. So the last bit that the last two bits I'm going to show are very briefly this tool called ProcMon. ProcMon is a sysinternals tool. It's free. It's available on the Microsoft site if you want to grab it. And in this case, we can monitor everything that a process does on this machine. And in this case, I'm going to just monitor the .NET exe process. And you could even see like registry accesses. I'm not interested in those for this demo. And so I'm going to run that, come over here, rerun my code, and then jump back here, stop monitoring. And you'll see a whole heap of stuff, if I scroll down, about this process when it ran, and it's pretty verbose. This can be quite useful, though, particularly if you ever run into like assembly load exceptions, or you run into things where you've maybe got the wrong version of a dependency seems to be being loaded. This will show you every file access that's happening as part of that process. There's a lot of repeat stuff here because it lists every kind of like OS operation, and there's a lot of stuff in reading a file that's more complex, like checking it exists and checking the attributes on it, etc. But we can see if we kind of quickly scroll down that we've got, obviously we go into .NET.exe, then those Windows sort of core files got used. Eventually, though, we start to see, can I zoom this? No, I can't. Let's use Windows Zoom again. Eventually, we see a bunch of stuff happening in this host FXR folder, which is that main container for those host fixer libraries. And what this is actually doing is we're seeing where .NET here is basically going through that directory, that known location, and saying, well, what's the most recent version of the host fixer that I've got for this application to run? And it's resolved the version 9 host fixer DLL. Host fixer then does a bunch of stuff. Eventually starts reading our DLL and also critically that runtime config file to say, well, what version of the runtime do you want to run on? There's a bunch of additional shared files that get checked, but then we see host policy is starting to be accessed. So that DLL is now being loaded into the process and being used. If we scroll down some more, a bunch of stuff we don't care about, we start to see, yes, it's loaded core CLR. So you can see the actual core CLR DLL version and where that lives, that it's actually chosen. Scroll some more. And now we start to see system private core lib again for the runtime of version 9 being loaded from the shared directory. Down here, then we should see our DLL now starts to be accessed because now we're in a position of actually running the DLL. And somewhere down here, we see the JIT kicking in. So it's kind of the same information we saw in WinDbg and might be not that exciting right now. But again, if you ever run into an app that's not booting for some reason, you actually want to just double check what actual DLL were you loading from where. This could be really useful for those kind of low-level problem-solving sort of exercises. So the last thing I'm going to do here, and I'll have to come up with a new folder name, is go back a level and make a directory here called template app2, just to be really exciting, and cd into that. And what I'm going to do this time is, this time we'll actually use .NET New to create a console application. Hopefully most people have seen the SDK commands that you can use at the CLI for .NET. Again, we're using the .NET.exe, and what it's going to do this time is it's saying, well, I haven't been given a DLL as my first argument, so I've been given some other stuff. How should I interpret that? And in this case, it's going to say, well, this is actually going to be something I need to hand off to the SDK. And if we jump back to my application, my .NET folder here, within the SDK for version 9, if I scroll down in here, there's a file in here called .NET DLL. It's about 2,800 kilobytes, and this is actually the SDK. The SDK for .NET, if you go to the GitHub repository for it, is mostly written in C# code. It's another managed application that just knows how to take arguments and do a bunch of stuff, and that's compiled down to .NET DLL and put into the SDK folder here. And so what that's going to then do is invoke that DLL, that .NET DLL, pass in these arguments, and then it's going to do whatever the SDK is told to do. In this case, create a new console app. I've done verbosity diag here because I want to see the output. So this basically gives us the log of what that command does behind the scenes. Not too interesting. We're not interested in much of this. I'll scroll to the top, which is quite long with this font size. And you can see that really what that's doing is loading into another part of that file in that assembly where there's a whole template engine that knows how to resolve what the template for console should look like for version 9 of .NET and load up and create the appropriate files in my directory. So now if we go down here, if I clear the screen and list what's in here, we'll see that indeed we have a program CS file which just contains the typical hello world console write line of a console app in .NET. We have a project file. We have an OBJ folder. The OBJ folder, we're not going to get too deep into it. This is really like the temporary build area for .NET users. So when we compile, for example, each file gets compiled and pushed into this OBJ folder. And that means that we get more advanced compilation, because later on, if we only modify like one file and then rebuild an app, we don't want to rebuild or compile every file. We just compile the files that change, and then those essentially get kind of linked together into the assembly that would then go into the bin folder later on. So that's what that folder has in it. We obviously have this project file here, so I'll open that up in Notepad. And typical project file, there's a small property group here that tells us this is an .exe, .NET 9, no, implicit usings are enabled as is nullable. But there's not much in here. And a project file is a file that's used by MS Build, the build system for .NET, to obviously build our code base. But there's not much there. So how does MS Build, know how to take this project file and build it, right? The key thing is that we're using modern.NET, so it's an SDK-style project format. And what that means is that there's an SDK that's defined in here that tells it, okay, the SDK you're using, in this case, is the .NET SDK. There's one SDK for like console apps and sort of basic worker processes and things. Then there's an ASP.NET Core one that has additional information for building ASP.NET Core applications. There's an Aspire one now as well, I believe. So this just lists the SDK. So what actually happens here, and we're going to use another command here, I'm actually going to invoke through .NET MS Build directly here. And if you actually jump back to this folder where we were in the SDK, if I come down, MS Build. So MS Build DLL, again, it's another C# file. Most of MS Build is written in C#, just gets compiled down to a managed executable that's loaded through the .NET Runtime itself. So MS Build is there, and it's accessible as an additional command that we can pass into .NET so that the muxer knows that in this mode I want to invoke MS Build. And what I'm saying to MS Build here is I'd like you to take this project file and pre-process it, which basically means expand it using the knowledge from the base SDK about what this actual build file should look like for MS Build. So I'm going to run that. I am, thank you. It's really nice having human co-pilots in the room. Right, we've pre-processed. I'll clear the screen and list. So we now have pre-processed.xml. So we didn't actually build here. What we did is just say, take a look at that project file and essentially expand it. And so if I open that in something like code, and zoom this in a little bit, this is a full XML that MS Build will actually take in for when we build that file. And you can see it's like 16,000 lines of XML. So no one wants to type that by hand, so hence why we have these simplified project formats that make our lives a lot easier. But where has a lot of this come from? If I search for implicit using and go to there, we'll find in here our property group that was defined in our actual CSproj file for this application. You can see that's in that template to CSproj there. So that's what we put in. Everything else in this file, and it's kind of telling us here, this import was added, so this import to sdk.props was added because the project's element SDK attribute specified Microsoft Net SDK. So the SDK directory, as you can see from these paths, includes these prop files, target files, all of the things that are the peripheral information about how to build these .NET applications. So we're obviously not going to spend too much time parsing through this. You can see a lot of these end up being conditional, so conditional on the type of project we're building or various other properties we might set within the project. Rather than explore the XML, which is not that exciting, what I'm going to do instead is do a build, but this time I'm going to do .NET build. I'm going to do a release build of this, and I'm going to pass in this additional argument at the end here. And what this argument basically says is, hey, when you're building, log out everything you do into this binary log format. And so we can run that. It's going to compile, and if we check, indeed we now have a bin folder. I could cd into that, and we can list what's in there. And you get what you'd expect in there, the DLL, the symbols file, runtime config, etc. Those have all been created for us. But the thing we want to explore is that bin log, right? So to do that, I'm going to use another tool, which I think also Kirill Ozenkov, who did that PE tree tool that I used earlier, I think he was behind this at Microsoft. This is the MS Build structured log viewer. And what this lets us do is open those log files. So if I go to NDC London, template app 2, msbuild.binlog, double-click that, and it opens up this human-readable sort of format that we can actually explore everything that happened as part of the build process. Again, this can be quite useful if you have really complex builds or more complex builds where weird things fail for some reason. You can do a bin log dump and then explore it in this file and actually just double check, well, what actually happened and in what order to compile this application and build it. There's a whole bunch of stuff in here. For example, we can see, if I expand environment, we can see all the kind of .NET related environment variables that were set at the point this ran, which can be really useful if you've done things like set a custom path for the SDK or something. You could double check in here why it's failing because you set the wrong environment variable, etc. What we're interested in, though, if I expand this node, so this was the restore step up here, but this is the actual build step next. And you'll see all of the targets then from that XML file that actually got run. So you can see a lot of these are grayed out because they were conditional and those conditions weren't met. But the other targets that are not grayed out give us examples of everything that was done in order to actually build this through MS Build. A more useful view, just to help us get started, is if we go to this tracing view. It's not particularly pretty. If you're used to OpenTelemetry tools or something, this is not nice. But it gives us essentially this view of what actually happened in the build and how long did it take. So we can see that actually core compile took 1.6 seconds, and that was the main compilation of this code base. And you can see that actually used CSC, the C# compiler. So if I double click on core compile, and why is that? Oh, we go. Actually, I probably don't. I'll keep it zoomed in just so you can see this properly at the back, which is really horrible to work with. So if I expand this target, this core compile target that was defined within that, we can see that actually it ran a task called CSC. And that's the task that defines how to launch the C# compiler. And so if I expand that, you can see that the actual code, this is really difficult. You can see the actual code for that task is defined in this assembly, part of the Roslyn code base. And again, the task that is actually invoked here by MS Build is another C# project. It's just a format that you can write tasks in for MS Build that conforms to a particular set of signatures, and then MS Build can invoke those for you from managed code. And that comes from this code analysis DLL. If I then look at the command line arguments that were passed in, if I double click this, you'll see that at the top here, we launched .NET.exe. Don't worry about the exec, but it's another way of launching an app. But the actual key thing here is that we see that same command that we used earlier on that invokes the CSC DLL. But then we have a lot of other stuff that we didn't put in our very simple example earlier on. And this is why you never want to compile manually through CSC, because here's all the other references we might need. This is just basically all the references for the base class libraries in case we use them. But there's a bunch of other flags and things that are set in there. So generally, you won't want to click close on that. You won't want to do that by hand. But that then sort of lets us see what actually happened there. How am I doing for time? Have a look. 3 minutes. 3 minutes, we'll very, very, very briefly talk about AppHost. So this is one other thing I wanted to show. So in our bin folder here, we have our DLL, we have the PDB, etc. But we also have an executable, a native executable that gets built. And where's that come from and what's its purpose? This is just a shortcut into launching our app. And the way this works is there's the same code base that actually compiles into that .NET.exe can also compile into something called AppHost.exe. And AppHost.exe is, there's a little bit difference in the code, but it's basically the same. AppHost.exe knows how to load hostfxr, to load host policy, and launch the runtime. And in the file that's produced that gets shipped with the SDKs, there's a kind of placeholder section at a particular byte location in that file that would be replaced with the DLL name that you should execute. And so what happens is the AppHost gets copied as part of the build process from the shared SDK folder. A few of its bytes get modified to replace the DLL that you should execute, which basically would replace it with this DLL name. And then this essentially just provides us a shortcut to do template app2.exe to run the application. So it's just a convenience, really. That means that when you're developing apps, typically, I can then run this exe on my Windows machine to launch the code, rather than having to type .NET and then the DLL name. Obviously, if you're deploying this, you can only deploy that to the same platform. It's platform dependent. It's an executable that runs on Windows x64 in my case. So it's useful usually in the developer experience. For deployment, you typically will ship the DLL and then use .NET to launch it in your code base. That is pretty much our time. So if I jump back to my other window here, just to highlight this link, so there's a bit.ly link here to smallest/C#. This will include links to, there's no actual slides, obviously, to share with you. I didn't use any. But the links take you to all of the blog posts that I've used as references when I've researched this, a few blog posts I've written during prepping this talk, and all of the tools, so things like the hex editor I've used, the .peek tool, etc., where you can go and find those to download. Otherwise, I won't do questions here, but I'm happy to take them afterwards. I hope you've enjoyed that. I hope it's been kind of interesting, if not necessarily useful for your day-to-day job. But just remember those tools exist, and they're there if you ever need to get into really low-level situations. Otherwise, thank you for coming.